We're going to sort of continue where we left off in the last class. A quick recap, what we've done so far. We've known that neural networks are universal approximators, but we must train them to approximate any function. And for this, we have to specify the architecture. We have to learn the weights and biases of all the neurons in the network such that it best represents the function that we want. The networks themselves are trained to minimize a total loss on the training data. And what we really want to minimize is the overall error across the entire space between what the network actually computes and what you want it to compute. And in practice, you can't really compute this error volume. So we sample the the input space, and we compute the average length of the errors. And the average length of the errors is a proxy for the total error, and that's what we're going to minimize. That's our empirical risk, right? We're going to use variance of gradient descent to do this minimization. The gradient of the error with respect to the parameters of the network is computed using backpropagation, which is what we're going to go through today. I have 255 slides for today. So if I actually go through it all, you're not going to go home till tonight. So we will stop somewhere in between and at some point next week, you will have an extra recorded lecture, maybe an hour long, which I will upload, and you're going to have to watch that just so you can pass your quiz. But anyway, so here's what we remember of gradient descent. In order to minimize any function, you start off at some point and you take a step in a direction where the function is going to decrease. And we saw why the direction of steepest decrease was the opposite of the, somebody fill in the word for me? The gradient, right? And because what was the gradient? The gradient was the direction of steepest increase, right? And you could keep doing this till the function basically stopped changing. Now there were a couple of different tests you could run to decide whether you must stop. One of them was to see whether the gradient actually flattened out. Was that a good function, a good objective? No, why not? Remember? Speak up. The gradient won't be zero at the boundaries. If the optimum is at the boundary, the gradient can be anything. We saw specifically for the Kullback-Leibler divergence that at the optimum, the gradient is actually, the derivative is actually 1 or minus 1. The slope is 45 degrees, right? So it's better to actually look at the function itself. And so here's how we defined it. We have this loss, which is the average error or the average divergence between the actual output of the network, y, and the desired output of the network. The parameters of the network, which are shown after the semicolon, are the weights for every single layer in the network. And so the gradient descent algorithm is going to do something like this. You're going to go for every training instance, you're going to go through the data and you will compute the derivative of the divergence with respect to the parameters of the network, and you would aggregate this over all of your training instances to get the derivative of the loss itself. And this you can just plug in to your gradient update rule, right? Now, this means we needed to compute this one term. What is the derivative of the divergence between the actual output of the network and the desired output of the network in response to a single input, right? And the derivative with respect to all of the parameters of the network itself. So this was just the same thing restated. But we saw that in the process, when we tried to work out this derivative, we found that we actually had to compute derivatives of each of the activation functions at the current value, right? Which means that because each of the activation functions works on some affine combination of inputs, and the derivative itself changes with the affine combination of inputs. The derivative is a function of the location where you're computing the derivative, which means you needed to compute this affine combination of inputs first. So you first had to, this is what we said is the first thing we must do when we terminated the class. So let's start right there. So here's the network. Remember how we actually visualize this network. You have the input, you have weights at every layer. We are still assuming it's layered. It's not necessary. Every layer has a bunch of neurons which have activation functions. So if I actually expand it out, I can draw it like so. So every neuron has an activation function which might actually change by neuron or by layer. You're keeping it very generic, right? Every neuron has a bunch of incoming connections, each of which have weights, and a bias which is accounted for by this additional one that we've extended each layer by, right? And the manner in which you perform the computation is that you first compute the affine combination of inputs for every neuron, and then you pass the affine combination of inputs through the activation for the neuron. So there's a two-step process in computing any neuron. First you compute the value z, and the z is put through the activation, and you compute the value y, right? So let's see how exactly this would be done algorithmically. For the very first neuron in the very first layer, the affine combination, now this parenthesis 1 tells you it's the first layer, the subscript 1 tells you it's the first neuron. This affine combination is the affine input z is simply going to be a weighted combination of all of the inputs. We are going to, for notational convenience, we're going to say that the input is the output of the 0th layer. So we just say y0, right? This is just for notational convenience. In fact, anytime you speak of an input layer, remember there are no neurons over there. This is just a notational convenience, right? And so yi of 0 is the ith component of the input, and then wi1 of 1 is the weight from the ith component of the input to the first neuron in the first layer, right? And so the affine combination is just going to be this weighted sum over all of the inputs, over all of the red arrows. So we would compute this for every single neuron in the layer. So the generic computation is going to be that the affine combination at the jth layer is going to be a weighted combination of all of the inputs, where the weights are specific to the jth neuron, right? The affine combination to the jth neuron in the first layer. And then once you've computed all of these z values, what is the next thing you do? You're going to put every one of these z values there through their corresponding activation. So the yj of 1 is the output of the jth neuron in the first layer. That's simply there is a result of applying the activation f1 on zj of 1, right? Subsequently, you can compute the affine combinations at the inputs to all of the neurons in the second layer. So here's the first step: affine combinations, the affine combinations that go into the activations of the first layer, the outputs of the activations in the first layer. Then the next step, you compute the affine combinations for the second layer. And obviously, the next thing that's going to happen is that those are going to be put through their activations, and you will get those values, right? And so on. Then you'd compute these affine combinations, and then those values all the way to the end. Eventually, you're going to get a bunch of affine combinations at the very output layer, and from those, you would compute an output. Now, remember that we discussed in the last class that neurons can actually have scalar activations or vector activations. When we spoke of vector activations, what it meant was that it got multivariate inputs and produced multivariate outputs, and you couldn't separate the individual components, right? So this entire computation is what we will call the forward computation. And if I have to write the algorithm down, it's a very simple algorithm. I'm going to initialize the y value at the 0th layer as the input, and then I just go through the layers. For each layer, I first compute an affine. For each neuron in each layer, I first compute this affine combination of the outputs of the previous layer, and then I put it through the activation, right? So in the process, we are computing every one of these z values, and these z values were what we required when we actually wanted to compute the derivatives, right? So this is what we will call a forward pass. We can write a little bit of pseudocode like so. I'll leave it on the slides. Now, once we have done this, we're going to have to remember all of these z values. Now we want to work our way backwards and we want to compute the derivatives. The way we will do it is like so. First, we're not going to compute the derivatives with respect to y. You're going to compute the derivatives of the error between what you want y to be and what y actually is. And this error is not a vector. Regardless of whether the network produces a vector or a scalar, the error itself is going to be a simple scalar number. So if you stop and think about it, this is phenomenal. I have this one simple real valued number, and this one simple real valued number is being used to learn millions of parameters, right? And you're mapping all of these millions. The network can literally have millions or even billions of parameters. All of them eventually produce this one single real valued number, the error, when you're trying to learn the network. Okay? So we have this divergence function, which quantifies the error between what you want the output of the network to be and what it really is. And then subsequently, we're going to work our way backwards. First, we will compute the derivatives of the divergence with respect to the output of the network itself. And then once we do that, we will use those derivatives, we'll use the chain rule and take a step back and compute the derivatives of the divergence with respect to the affine combinations that go into these activations. And then we will take a step back and compute the derivative of the divergence with respect to all of these weights, which are the weights of the neurons in the final layer. Then you take a step further back, and you're going to compute the derivative of the divergence with respect to the outputs of the penultimate layer. And then you would take a step back and compute the derivative with respect to the affine combination that goes into the penultimate layer, and then the weights for that layer, and then the output of the layer before that, the input of the layer before that, and so on, until you go all the way to the input. Right? So now let's actually see the math. This is why we call it, this is called backpropagation, because you're taking the derivatives and you're computing the derivative of the divergence with respect to all of the parameters in the network, but you're starting from the end and working your way back to the input. And we call it error backpropagation for a very specific reason. When you use L2 as a divergence, the derivative actually has a component which is exactly the error, right? More generally, you're not going to get this nice clean error term, but we still call it backprop or error backprop. So let's look at how these derivatives themselves would be computed. It's actually fairly straightforward. You have some divergence function, and we're going to assume the divergence function is differentiable, remember? And so the divergence function is differentiable. I can compute the derivative of the divergence with respect to each of the inputs to the divergence function. The inputs to the divergence function are both the desired output D, but that we don't really worry about changing, and also the output of the network. Now, here's an interesting thing that perhaps you never thought about. You can even ask yourself the question, how must I change the label that I assign to this input so that it matches the network? And this is something that you actually end up doing in some cases, right? That's when you would actually need the derivative with respect to D. But for now, D is fixed. This is what this target output is. And so you can compute the derivatives with respect to the output of the network. Derivative of divergence with respect to all the y terms, yes?
Why would you want to change the label of the output?
For some crazy experiment which has nothing to do with what we're covering today. But if you're curious to know what the label of this data instance must be to best match what the network predicts it must be, then you'd be mucking around with that, right? Anyway, so as a first step, you would compute the derivative of the divergence with respect to the output of the final layer, which is simply the derivative of the divergence with respect to each of the components of the output, right? Subsequently, I can compute the derivative with respect of the divergence with respect to the affine values going into each of these neurons, right? And by the chain rule, the derivative of the divergence with respect to z is simply going to be the derivative of the divergence with respect to y times the derivative of y with respect to z. And now, since you're working your way backwards, this first term has already been computed. All you need is the second term, and that second term is simply the derivative of the activation function itself, right? Computed at the current z. And so this whole thing collapses very simply to the derivative, this term, the derivative of the divergence with respect to the affine inputs to the activations of the final layer are simply going to be the derivative of the divergence with respect to the output times the derivative of the activation function itself. No fancy math here, right? Then I can take a step back, and now I want to compute the derivative of the divergence with respect to the weights, because this is what I want in order to actually perform my gradient descent, right? Now what is the derivative of the divergence with respect to the weight? That's going to be, using the chain rule, the derivative of the divergence with respect to the affine combination z times the derivative of z with respect to the weight. And this first term has already been computed because as you work your way backwards. The second term, now remember that z is simply, if you take just say w11, z is w11 times y1, where y1 is the output of the previous layer plus some additional terms, right? So if I take the derivative of z with respect to w, it's just going to give you this output, the output of that particular neuron that is connected to by the weight, right? And so in this case, this derivative of the divergence with respect to the weight, which is simply going to be this guy, which is the output of the neuron in the n-1th layer, and this has been computed in the forward pass, right? And so you could do this for every one of these weights, and subsequently, so I can just plug that into the formula, and you can compute this for every one of these weights. You can also do this for the bias term. For the bias term, all you're going to assume is that this y value is 1, right? The math doesn't really change. No questions, right? You know this guy, you know this stuff. You've been doing backpropagation. Now, next, how do I actually compute the derivative with respect to the outputs of the neurons on the penultimate layer? Now, here's where it gets a little more complex. Remember, we drew these influence diagrams, and this principle is going to come back, and we're going to use it again and again. If I have some x and I have some y, and y equals f of g1 of x, g2 of x, and so on, then this was g1, g2, g3, g4. You could draw the influence in this manner, remember? And when I draw the influence in this manner, the derivative of y with respect to x is going to be the sum of the derivatives down each of these chains. And we saw why this must be so in the last class, correct? So this really means that when I compute the derivative over here, the derivative of the divergence with respect to this y, observe the black lines. There's actually a nice little influence diagram over there, right? There are two things going on. So that means I'm going to have to sum over all the incoming lines to y, or rather I can think of summing over all of the edges going out of y, right? And so the derivative of the divergence with respect to this yi is going to be y1 is going to be the derivative of the divergence with respect to the first z times the derivative of z with respect to that z with respect to y, plus the derivative of this divergence with respect to the second z times the derivative of that z with respect to y, and so on. It's summed over all the paths, right? And so and this term, of course, has already been computed as you work your way backwards, and we know that these terms are just the weights because z is an affine combination. So you get this nice little formula, and here is the interesting bit that falls out. that the derivative of the divergence with respect to these y's is an affine combination. In fact, it's a linear combination of the derivative of the divergence with respect to the subsequent z's. Right? See the analogy between the forward and the backward pass? The z's were an affine combination of the y's. The derivatives of the divergence with respect to the y's are an affine combination or a linear combination of the derivatives with respect to the z's. And the weights in the two cases are the same. Right? And now I can do this for every single z over here, y over here, and then I can take a step back. So that's the formula, right? And now I can take a step back and say what is the derivative of the divergence with respect to the z's, and using the same approach, that's going to be the derivative of the divergence with respect to y times the derivative of y with respect to z, which is simply the derivative of the activation at the current point, right? And then you can use the same, and then subsequently you can work your way backwards, and you can compute the derivative of the divergence with respect to each of those weights, which is simply going to be, so for any given weight from say y to some z, right? If this is a w, the derivative of the divergence with respect to the weight is going to be the derivative of the divergence with respect to z times this y, because z is a reciprocal, combines the product of y and w, right? So that's basically, that simply gives you this very simple formula. You're computing the derivative with respect to z and then just multiplying it by the y at the beginning of the connection, right? At the beginning of the edge. And then you can work your way back, compute the derivative with respect to the y's, go back, compute your derivatives with respect to the affine combinations, and so on. Eventually you're going to get your derivatives all the way with respect to the weights at the very first layer. Now the math itself is very straightforward. There's nothing particularly complicated about it. If one were to write the pseudocode for it, here's what it would look like. We're going to just initialize the derivative of the divergence with respect to the outputs of the network, which is basically the gradient of the divergence with respect to the output of the network through direct combination, direct differentiation, right? And subsequently, we can take a step back and compute the derivatives with respect to the affine combinations at the inputs, at the output layer. And then you just work your way backwards from the final layer to the initial layer. There's a three-step process. First, you compute the derivative of the divergence with respect to the y's, which are the outputs of the layer. And that is simply an affine a linear combination of the derivatives with respect to the z's, right? And then you can take a step back and compute the derivatives with respect to the z's themselves, where you're just going to be multiplying the derivative with respect to y by the derivative of the activation. And as a side step, you're going to be computing the derivative of the divergence with respect to each of the weights. And that's simply going to be the derivative with respect to z times the y, right? This is just going backward. Very simple algorithm. And if I were to write it in pseudocode, this is the so-called backward pass. Here's what you do for any given input. You have this two-step process. First, in the very first step, you're going to compute the derivative of the divergence with respect to the output of the network, and then take a step back and compute the derivative with respect to the affine combination at the output of the network, right? And then look at what happens. The two steps are, you compute an affine combination or linear combination of the derivatives at the input to the next layer, right? And then multiply that by the derivative of the current activation. As a side step, you also compute the derivative of the divergence with respect to the weights. Now, if you look at this pseudocode looks a whole lot. So here's what we got. It's very analogous to the forward pass. In fact, if you were to write a generic piece of code, you could write a forward pass code and just replace two lines of code, and you're going to get your backward pass, quite literally, right? And that's the magic of the whole thing. So look at this. What's happening? As you go back, the only special thing is the derivatives at the outermost layer. But then we did a similar thing when we were doing the forward pass, where we equated y0 to x, right? So you have to treat the boundaries specially. And then as you go backwards, you first compute a weighted combination of the terms at the next layer, except when you say the next layer, it's the layer in front of you. And then the weighted combination, instead of simply being put through a function, it's being multiplied by the derivative of a function, right? You can also think of this as some crazy function over here. And so if you look at this pseudocode and look at the forward pass pseudocode, look at what's happening in the loop. In the forward pass, first you're computing you're going left to right. First you compute an affine combination, then you put it through a nonlinear transform. Here, first you compute an affine combination, then you put it through a nonlinear transform. It's exactly the same operation, right? The only thing is that in the backward pass, you have this extra step where you're computing the derivative with respect to the weights. So, questions? We're going to sort of fly through a few more things. I'm assuming this is all very clear, right? There are some special cases. We've made some assumptions over here. The first assumption is that the computation of the output of one neuron does not directly affect the computation of the other neurons in the same or the previous layers, right? That every neuron is independently computed, and that the derivative of every neuron doesn't depend on the derivative of other neurons, right? That the outputs of neurons only combine through additive combination. We just assume that the Z is an affine combination of the outputs of the previous layer. These are assumptions we're making. And we've also assumed that the activations F are differentiable everywhere, right? All of these can be violated. So we make these assumptions. This is the simplest kind of model you can think about it, but all of these can be violated. We have information about how these things can be violated in the slides. So please go over it, because we'll invoke this in the quiz, just to make sure that you've gone over the slides. What it means to violate every one of these three criteria is something that you must be familiar with, because this will come back in various kinds of neural networks that we will see through the course. The one special case I'm going to talk about is vector activations. Vector activations where all outputs are functions of all inputs. So I could have y1 through yn equals function of x1 through xn, where I cannot separate out the individual components. This is a vector activation. And we have seen, so this is different from a scalar activation. In a scalar activation, each y is a function of one z, right? In a vector activation, every y depends on every z. So you can't really separate the activation out like so. So in this case, if I draw the influence diagram, this is what it's going to look like. When the activations are scalar, each y is dependent only on the corresponding z. If the activation is a vector activation, each y depends on every single z, and conversely, every z influences every single y, right? So in this kind of situation, if I have the scalar activation, so this backward pass is very simple, right? If I want to compute the derivative of the divergence with respect to z, I can do this individually for every one of my neurons. For each neuron, I compute the derivative of the divergence with respect to y, and then multiply it by the derivative of the activation function. Very straightforward. But then if I have this vector activation, here's what happens. Every one of those y's influences the divergence, right? And any given z influences every single one of those y's. So using the same principle that we had out here, here's what we're going to get. If I want to compute the derivative of the divergence with respect to just say the z on top, I'm going to have to compute the derivative of the divergence with respect to each y, and then the derivative of each of those y with respect to that z, and add them up, just following this lines of influence. Make sense, right? And so we'll take a look at one special case. We have vector activations and other special cases on the slide, but let's look at one thing. This is the softmax. We've seen the softmax previously. Now observe in the softmax how every z affects every y. So let's say I increase z1. What happens? The corresponding output exponent of z1 increases, but then I'm normalizing it by the sum of all of the exponents. The other y's will decrease, right? So changing any particular z is actually going to, so I have in the softmax I have z1, let's say I have 3 z's, z1 through z3, and then each of these guys in turn also influences every single output. If I increase this guy is going to increase, but these two guys are going to decrease, correct? So if I think of a derivative, right? An incremental increase in z is going to increase one y, it's going to decrease the other two. Remember, derivatives are all about the effects of incremental changes and the input, right? And so if I want to compute the derivative of the divergence with respect to any given z, what is it going to be like? This is exactly the formula that we saw earlier, right? It's going to be the derivative of the divergence with respect, I'm going to sum over all the y's. It's going to be the derivative of the divergence with respect to the y times the derivative of the y with respect to z, summed over all the y's, right? And so the thing that really matters is what is the derivative of yj with respect to, say, zi, where you're given yj equals exponent of zj divided by summation I exponent of zi, right? There are two cases. So the two cases are, what is the derivative of this guy with respect to this one, which is in the same line. The other case is, what is the derivative of one of these guys with respect to this one, which is a different line, right? So in these two cases, let's consider the first one. So this is going to be derivative of yi over derivative of zi is going to be the derivative of e raised to zi over zi times 1 over summation j e raised to zj, right? Plus e raised to zi times derivative of d over dzi of 1 over summation e raised to zj. Just a standard differentiation rule, correct? And the derivative of the exponent is simply going to be, this is simply going to be e raised to zi over summation j e raised to zj, because the derivative of an exponent is itself. For the second guy, that is going to be plus e raised to zi, this didn't change, times, and now because this is in the denominator, it's going to be e raised to zi over summation j e raised to zj squared minus, right? And I'm assuming you can see that. So that's going to be, so this is dyi by dzi is going to be e raised to zi by summation j e raised to zj minus e raised to zi by summation j e raised to zj whole squared, which is simply going to be yi minus yi squared, right? This is for the straight line. For the cross, that's for this guy, right? The one on top. What about the cross line? For the cross line, that's going to be simply dyi by dzj, where j is not equal to I. This is going to be derivative of e raised to zi over zj. This will be 0 times 1 over summation j e raised, let's use k over here, zk, plus this is going to be e raised to zi times d of 1 over summation k e raised to zk by dzj. This guy is 0 because this is not a function of zj. This goes away. All that remains is this term. That's going to be e raised to zi times minus of e raised to zj divided by summation k e raised to zk squared. That's going to be minus e raised to zi over summation, the summation term, times e raised to zj over the summation term. That's equals minus yi yj, right? Simple. Nothing particularly complicated about this arithmetic. But the point was the derivative in the straight line had one property. The derivative in the second lines had a different property, right? And so if you work this, if you just write it out, here's what it's going to look like. The derivative of any of a y with respect to a z is going to be y times 1 minus y if I equals j, right? And it's going to be minus yi by j if I not equal to j. We just sort of work this out, okay? So I can write the derivative of the divergence with respect to any given z now compactly as follows. I'm going to sum over all of the i's. So in fact, these two formulae can be written jointly like so. I can just say this guy is, I can write this as yi times delta ij minus yj, where delta ij is the Kronecker delta. It's 1 if I equals j and 0 otherwise, right? And so you can see why this is going to be positive for I equals j and negative for everything else, right? So this term is guaranteed to be positive because yi is less than 1. So yi squared is always going to be less than yi. So the derivative along the straight line is always guaranteed to be positive, which tells you that if you increase a zi, the corresponding yi increases. The derivatives for the others are guaranteed to be negative because if you increase the zi, the remaining yi is decreased, right? The information comes out. And so the derivative of the divergence with respect to any given z has this nice little compact formula. Again, that was just one example of a vector activation and how the derivative actually changes, right? So the overall approach for computing the derivative of for gradient descent to learn a network is for each data instance you have a forward pass, you pass it through the network, you have a backward pass, you sweep it back through the network and iteratively compute derivatives with respect to all the parameters. The actual loss, of course, is the average of the divergences over the entire training data. So the actual gradient is the average of the gradients for each of the training instances, and you're just going to use this gradient in the gradient descent rule, right? So the entire pseudocode. Now when we write this in scalar form, it looks really ugly. I'm working through each piece of arithmetic, I'm writing loops. I mean, it's not that ugly, but it's uglier than it needs to be. It's much more convenient to think of it in vector terms, particularly when the network is layered. Well, for layered networks, the vector arithmetic is not only simpler to visualize, it turns out that you can actually exploit parallel processing abilities, which is why we use GPUs, right? And you can do the whole thing in vector arithmetic. You can restate the entire process in vector terms, and this is what is actually used in a real system. Every time you write code, you're using tensors and vectors, right? So how do you do this for vectors? Consider this. I can put all of my x's in one vector, x. All components of the input as one vector x, right? I can put all of the z's, all of the affine combinations going into each of my neurons. I can connect them up into one vector z, and then I can have the y's, which are the outputs of these activations, also written as a vector, right? Now I can write out all of the weights. I can write out the set of all outgoing weights from each neuron as a row vector. So over all of the neurons, every neuron over here, in this case these are not really neurons, these are inputs, I'm going to have a row vector. I can stack them up and that becomes a weights matrix. So for example, if you look at this guy, this set of weights, this is the last row in the matrix, is going to be the set of weights going out from the last component over here arranged as a row. And now when you multiply W by Y, in this case X, what happens? You're basically getting the, you can actually write, similarly I can write the biases for all of the neurons as a single vector, B, right? So now when you write, so if I write out the arithmetic for how Z is computed now, it's fairly straightforward to work it out, right? That you're basically, when you write out W times Z, you're going to get, let's write this, it's worth the trouble. So if you look at WZ, each component is going to be summation Wij, right? Wx, right? Or Wyk minus 1 in general. Yk minus 1 is going to be Wij Yk minus 1 j. You're basically getting a summation, right? And so when I write W times, so I have added this, I missed this. I have the subscript k, which tells you which layer the weights are for. So Wk is the matrix of weights going into the kth layer. Yk is the set of neuron outputs in the kth layer. Zk is the set of affine combinations going into the kth layer of neurons, kth layer of activations, right? And so if I can, when I write Wk Yk minus 1 plus Bk, this is simply going to be a set of terms where every term is going to be summation Wkij, summation over j, oh wait, no, summation over I, j. You have to be careful about the indexing, right? The way it's written is I. It's going to be Yi k minus 1 plus Bk of I of j. Each term ends up being just this, which is basically just the affine combination that you're looking for, right? So the point, of course, is it's not the mess on the board. The concept is fairly trivial. And then once I write it like so, I can write the output of the white layer as just some activation applying, operating on the affine vector z, right? And so having written things in this manner, the forward pass actually becomes really trivial for me to write. I'm going to set y0 as the input. Then z1 is simply going to be w1 times, should have been y0 plus b1, right? And then I'm going to say y1 is simply the activations in the first layer operating on z1. Then z2 is going to be just w2 times y1 plus b2, right? And then the output of the second layer is simply going to be the activations applying on z2 and so on. I can work my way all the way to the end. Now in the process, observe something. There was something else that was actually being written below. For the first layer, I first computed the weighted combination of inputs, applied an activation. For the second layer, I computed a weighted combination of these guys and a second bias, applied a second activation, and so on. So the entire network is basically just a nested function. Every layer is a function that operates on the output of the previous layer, which is also a function. So the network itself is just one deep nested function, right? And the entire forward pass can be written in vector form in this really trivial format, which is to say I just say y0 equals k, and then I go through the layers, and two little formulae are going to take care of the entire operation for me, which is somewhat simpler than the notation we used when we were trying to write this in scalar form, right? And so here's the forward pass, much cleaner than the scalar version. What about the backward pass? It turns out the backward pass is equally simple. First, we need to compute a divergence, the divergence between the output and the desired output. The divergence is a function of the output of the network Fn which in turn is a function of fn minus 1 and so on. So the divergence is also a nested function, right? And when we begin thinking, and except now, the divergence is a scalar function of many variables, which are both vectors and matrices. The biases are vectors, the weights are matrices. The divergence is also a function, scalar function of the scalar, the vector affine combinations, the z's. It's a function of the y's, right? So here's a simple calculus recap. You remember we mentioned the Jacobian at some point. Now, how does the Jacobian actually come to be? The Jacobian, remember how we define the derivative. If I write a function y equals f of x, the derivative is simply this multiplicative term that multiplies, okay, in this case y equals f of z. The derivative is simply this multiplicative term that multiplies a small incremental change in z to give you the corresponding incremental change in y. It's still the same definition, right? So if you look at this guy now, look at the equation over there. y1 is a function of a vector. It's a scalar, right? The first component y is a scalar. What is the derivative of the first component of y with respect to z? It's a row vector, right? So I can basically stack up the derivatives of each of my y's, and that's going to give me my Jacobian. And it's very easy for you to verify that now when I multiply the Jacobian by delta z, it's going to give me delta y, the incremental change in y as a consequence of an incremental change in z. Now I'm using a specific notation over here. This is the derivative of y with respect to z. I put the z in the parentheses. The y is the subscript. That's simply for us to indicate that it's actually a function of the current location of z, right? So the Jacobians can describe derivatives of neural activations with respect to their inputs. If you have scalar inputs, then the derivative of any y with respect to the other z's is 0, right? So if the scalar activations are scalar, then this Jacobian matrix is going to be strictly diagonal. If the activations are not scalar, if the activation is a vector activation, so it's just going to, this is dy over dz, which is going to be the derivatives of the individual activations, right? If the activations are not scalar, the Jacobian matrix is going to be a full matrix. But then as far as we are concerned, we don't really need to distinguish between full matrices and diagonal matrices. They're just matrices. It's very convenient for us in the vector notation because we are not distinguishing between vector and scalar activations. We are just saying each z is an affine combination of the previous, is an affine transform of the previous y's. Each y is some activation. Each y vector is some activation that's applied to the z vector. So as far as we are concerned, the two are strictly equivalent. Now, for affine combinations, affine functions, if I have z equals wy, then the Jacobian of y of z with respect to y is simply going to be w. It's very easy for you to check, right? This is an incremental change in y is going to result in an incremental change in z. So delta z is going to be this Jacobian times delta y, right? What is the Jacobian of z with respect to b? Over here. Anyone? It's just the identity matrix. An incremental change in b is going to result in an exact same incremental change in y, right? Now here's the other thing. We can apply the chain rules even to vector functions. So let's say y is a vector which is a function of g. So y is a vector which is a function of g, which is also a vector, which in turn is a function of x, right? So then I can write g equals, so if I do that, I can write z equals g of x, y equals f of z, right? And by using our own rules, delta z is going to be the Jacobian of z with respect to x times delta x. There it is. it under my foot. The clip is gone. Oh, here it is. Just hang on, guys. I think I got it. Am I getting it? Okay. So to go back, now I can say z equals g of x, y equals f of z, right? I've just broken this down. And using our rules, delta z is just the Jacobian of z with respect to x times delta x. And delta y is the Jacobian of y with respect to z times delta z. So y equals f of z, that gives us this formula, right? And z equals g of x, that gives us the first formula. I can plug in the delta of z over here from this guy. Observe that all of the dimensions match, right? And so when I plug it in, I have delta y equals the Jacobian of y with respect to z times the Jacobian of z with respect to x times delta x. So now if I give you this one, if I ask you what delta y equals the Jacobian of y with respect to x delta x, what is the Jacobian of y? The Jacobian of y is simply going to be, with respect to x, that's simply going to be this product, right? Again, the chain rule works very cleanly. But in this case, when you're looking at the chain rule, there's something important. It's the order of the operations. Left multiplies are different from right multiplies, right? So what is the order in which things happened? First, you had the Jacobian of the outermost function. Then you had the Jacobian of the argument. And if it's chained many times, it's going to be the Jacobian of that argument and the Jacobian of that argument always multiplying to the right. Otherwise, your dimensions won't work, right? So what if y is a scalar? If y is a scalar, then, so let's see. In this case, let's assume y is a scalar. I'm still going to write z equals g of x. So z is still a vector, right? What is the derivative of y with respect to z? Is it a vector? Is it a matrix? Is it a scalar? What is it? In this case, what's it going to be? What kind of vector? It's a row vector, right? So it's a row vector. So the derivative of y, let me just write it as in the same way, the derivative of y with respect to z is going to be a row vector, dy over dz1 and so on, correct? And what is the derivative of, so this is the transpose of the gradient, this is the derivative of the y with respect to z. And what is the derivative of z with respect to, so I have delta y equals the derivative of y with respect to z times delta z, as before. And what is the derivative of, what is delta z? Now z is a vector, x is a vector. So what would delta z be? Just exactly what we wrote earlier, right? That's going to be the Jacobian of z with respect to x times delta x, right? And observe that the dimensions match. This is a row vector, this is a matrix. What's the product of a row vector and a matrix? It's a row vector, right? And so what is the gradient of y with respect to x over here? Or what is the derivative of y with respect to x over here? That's going to be this term, right? This product. So even if you're looking at a scalar, if I say d equals f of g of x, the same property holds. I can still compute the derivatives exactly as before. If it's a vector function of a vector, then the derivative is going to be a matrix. If it's a scalar function of a vector, the derivative is going to be a row vector, and so on. And I can keep multiplying the derivatives left to right using the same chain rule, but now the direction is important. I go from the outermost function to the innermost function, and in this process I go left to right, right? So one final term over here, if I have some d equals f of an affine function of y, then in this case z is simply wy times b, right, plus b, right? So the derivative of d with respect to z is simply going to be the derivative of d with respect to y is simply going to be the gradient of d with respect to z times w. This is just a straightforward application of the previous rule. We also know that the gradient of d with respect to b is simply going to be the gradient of d with respect to z, because z and b are identically related in terms of changes, right? There's one final kink over here. So when I write, if I have something of this kind, I have a vector and I have a matrix, and then I have some term over here, and then all of these go into a scalar, right? So this is W, this is A, in this case Z, this is Y. If I take the derivative of d with respect to W, something interesting happens. The actual operation ends up involving tensors which occur in this proper left to right formalism in exactly the manner that we've been talking about. But then if you rework it, what you end up with is going to be that the derivative of d with respect to W is going to be y times derivative of d with respect to z. So it's this guy times the derivative of this with respect to this term. The derivative of d with respect to z is a row vector, right? And then you can see that the dimension of this derivative is exactly the same as the dimension of W. The left dimension is the same as the dimension of y. The top dimension is the same as the dimension of z. Right? This is the one special case that we're going to have to handle. Okay? So given this, now how do I do my backward pass? It's trivial. I've defined all the necessary operations. So first step, I can directly compute the gradient with the derivative with respect to y. We just know exactly how to do this. This is just a standard gradient computation, right? Then if I take a step back, that's just the chain rule. So the derivative of the divergence with respect to z is going to be the derivative of the divergence with respect to y, which is right multiplied by the derivative of y with respect to z. And what is that? That's just the Jacobian. Right? Yes?
There's a question on the answer. Why is affine function described as a special case when considering Jacobians?
So over here, the only reason I'm talking specifically about affine functions is that affine functions are what we are using in the network. So the question was, why am I treating affine functions separately? Affine functions happen to be a special case for the network, right? That's all. So over here, so this, the derivative of the divergence with respect to z is simply the derivative of the divergence with respect to y times the Jacobian of the activation. If it's a vector activation, you're going to get a full Jacobian matrix. If it's a collection of scalar activations, you'd get a diagonal Jacobian matrix, right? And then here's where, in the next two steps, you will see why I'm treating the affine function specially. What is the derivative of the divergence with respect to y? The derivative of the divergence with respect to y is the derivative of the divergence with respect to z times the derivative of z with respect to y. I'm just chaining it back. The derivative of z with respect to y, z is an affine function of y. This is simply the weights matrix. Right? And so this one is simply going to be this guy. And at the same time, I can also compute the derivative of z with respect to the bias, which is simply the derivative of the divergence with respect to the bias, which is simply the derivative of the divergence with respect to z, and the derivative of the divergence with respect to the weights matrix, which using this rule is going to be the product of the previous y and the derivative of the divergence with respect to the following z. Right? Simple enough and straightforward. And then I can take a step back. What is the derivative of the divergence with respect to this y? This z. That's going to be the derivative of the divergence with respect to the y times the derivative of y with respect to the z, which is simply the Jacobian, right? That's just a bunch of activations. So this one is going to be the derivative of the divergence with respect to y times the Jacobian. And the Jacobian will typically be diagonal if you have scalar activations. And the final layer, it tends to be a full matrix. In previous layers, it tends to be diagonal. This is not required. I mean, you could actually have scalar activations even in intermediate, vector activations even in intermediate layers. And then, of course, so that's that formula. And then you can work your way back and compute the derivative with respect to that y, which is simply going to post multiply the derivative with respect to the z by the intermediate weights matrix, right? And you can also get in the process the derivative of the divergence with respect to the biases and the weights of that layer. So you can just keep going back all the way to the front. So the overall rule for backpropagation in vector arithmetic turns out to be very, very trivial. You start off by first computing the Jacobian of the for each of the layers, and you either you sequentially multiply by the Jacobian and then by the weight, and then by the Jacobian and then by the weight, and then by the Jacobian and then by the weight, which is just a bunch of straight up matrix operations. Somewhere on the side, as a somewhat of a byproduct, you also get the derivatives with respect to the weights and biases, right? And once again, you can see even in vector form how this is very strictly analogous to the forward pass. The forward pass, you first compute an affine combination and apply a transformation to it. Here you're computing, instead of an affine combination, it's a linear combination, except instead of left multiplying by weights, you're right multiplying by weights. So the difference between the forward and the backward pass now is that left multiplication is replaced by right multiplication. So you can't really use the same code. It needs to change, right? So here's the overall algorithm here. This is just for reference. So if you were to set yourself up, we've seen this slide before. If you wanted to train a binary classifier, is this a 2 or not a 2? Then you're going to define your training data, which is a collection of images in this case, which will be vectors, and labels, which will be 0 or 1. And because it's a binary classifier, the output is going to be a single sigmoid. And you can use backpropagation. If you're trying to train a digits classifier, then the output is going to be so the training data is bogus. That should have been fixed. So the label for each digit would actually be a 1-hot representation for the digit. The output layer is actually going to be a proper softmax, right? But everything else still holds. So there are some issues. How well does it learn? Can you improve how quickly and how well it learns? Will it generalize? What does the output really mean, etc.? We will get to that. But before that, there are other issues, right? Before, we've just sort of gone through the whole backpropagation. Here is a key solution, a key question. Does it always work? So you have convergence of gradient descent. You have so we're going to, first question is, does it always work? Secondly, how quickly does it get to the answer? What are the restrictions? How fast can you converge? Remember, you're looking at gradient descent with steps and such like. So we'll look at different variants of gradient descent that will make it get to the solution quicker, and whether we can how we can modify this approach to make it incremental, and some speed up extensions. But the first question, does backprop always work? So meaning, here's a different question. Let me put it differently. So if backpropagation actually finds the global minimum of the divergence function, or even a local minimum of the divergence function, is the solution that it gives you what you want it to give you, right? So here's what happened. In classification problems, the classification error is a non-differentiable function of the weights. The divergence function is minimized, that you minimize is not really the classification error. It's a proxy for the error, right? You made it differentiable. So which means what you're minimizing is not what you want to minimize. If you wanted an error, the error was 0 if you got it right. It was 1 if you got it wrong. So for example, if you wanted a label y, then if the output was exactly y, if the output was exactly 1 hot, 0, 1, 0, 0, 0, 0, then the error is 0. Otherwise, the error should be 1. But that's not what we are using, right? We are using the Kullback-Leibler divergence across entropy, where as you go away from the correct answer, the error gradually increases. And the reason we wanted to do that was that we wanted the function to be differentiable. This has a consequence. So this is a very nice paper by Brady and Raghavan and Sloane in 1989, way back when. Here is this collection of data, and we have two cases. In one case, I'm going to use the perceptron algorithm. Remember, the perceptron algorithm assumes threshold activations, right? And the other case, I'm going to use backpropagation, assuming a segment. In both cases, the classifier is linear. In both cases, the optimal classifier is that line shown over there, regardless of whether I use the perceptron algorithm or backpropagation. I'm going to find the correct answer. Now there are literally, in my example, hundreds of red points and hundreds of blue points, and then I add one more guy, just this one guy, right? So I have hundreds of red points out there, hundreds of blue points out there, and then I add this one red guy way close to the blue line. Will the perceptron algorithm find a solution? It will. The classes are linearly separable, right? It's going to find a vertical dotted line. How much will the objective function that I'm minimizing for backprop change? I have thousands of points contributing, and then I added one more point. Is it going to make a tremendous difference to the function? It really is not, right? So what will backprop find? Backprop is probably going to give you that guy, right? So in the limit, if I don't have any constraints on weights, eventually if I say the weights can go to infinity, then the backprop will can find a solution. But typically that's not what you really want. There is a solution even where the weights are not infinity, and backprop won't find it, right? So here's a case where the problem is solvable, a solution exists, one algorithm will find it, the other will not, right? That just goes to tell you that backpropagation is not solving the same problem that you want to solve. It's not going to necessarily find the solution that you want to find. Question is that a good thing or is that a bad thing, right? So let me flip this one spoiler, they call it a spoiler, and put it out there. What will happen with the perceptron algorithm? The perceptron algorithm is going to give you the dotted blue line. Backprop is going to give you the slightly shifted red line, right? As I keep moving this dot around, you will find that in every single case, the perceptron algorithm is going to swing around and give you the correct answer. Backprop is going to move just a little bit and will not give you the correct answer. Is this a feature or a bug? Feature, why?
Like, you don't want slight variations in your data which could be because of noise to actually change your answer by a lot.
Exactly, right? You don't want little bits of noise in your training data to completely destroy what you learned. So while I presented this as a bug, it really is not. It's a question of you heard this term, bias variance trade-off, right? I'm comparing the perceptron learn rule with backprop, which has the lower bias. In every case, the perceptron rule is finding the correct solution. It doesn't have a bias, right? Backprop is not finding a solution. It's biased. It's biased towards having an answer in the center. But which has the greater variance? The perceptron rule is just swinging wildly just by changing one little point, right? Here's a beautiful instance of bias variance trade-off. And so the perceptron rule can change greatly upon adding just a single new training instance, but it fits the training data well. So it has low bias, it makes no errors if it's possible to learn something without errors, but it has very high variance. It's going to swing around wildly in response to small changes in the input. So on the other hand, Backprop, it's minimally changed by adding new training instances. It prefers consistency over perfection. It's a low variance estimator, but it comes at the cost of potential bias. Make sense, right? So, and it's not just for linear classifiers. I don't have to stay with perceptrons. I can go with something with a nonlinear classifier. Suppose I have a decision boundary of this kind, right? Now, and suppose I have an optimal classifier in an architecture which can classify this. If I use threshold functions and if I use a greedy algorithm or an exhaustive search with the perceptron rule, if I add one little dot like that, that's going to swing the classifier around and it's going to learn to separate the red dot. Backprop, not very much. It's going to change a little bit. So is this a bug or a feature? We don't really know, right? Because there are situations where this extra dot is actually a very informative little dot. There are other situations where it really is not. And so we are taking a stand in favor of lower variance at the cost of bias. Now, going back and thinking about your various activation functions. Remember, we had this business of how much the activation function informs about how far you are from a boundary, right? Can you take a guess about which activation functions favor bias and which ones favor variance, low variance? Or which ones favor low bias and which ones favor low variance? We've just seen the example, right? Yeah.
I'm guessing the leaky ReLU has the lowest variance.
Some things like the leaky ReLU are going to have lower variance than a threshold function, right? On the other hand, if threshold functions, if you can use threshold functions, they're going to chase the latest training data. Now, this is just at an intuitive level. It doesn't necessarily mean it holds everywhere, but if you begin wondering about the behavior of whatever network you're training, you might see some answers there, right? So backpropagation will often not find a separating solution, even though the solution is within the class of functions learnable by the network. This is because the separating solution is not a feasible optimum for the loss function. One resulting benefit is that Backprop has lower variance than an optimal classifier on the training data. And lower variance is actually a good thing. Now, there's a lot more to it. Right? Here is a second issue. The loss function, we are using gradient descent, which means the way it operates, you start off at some point, and then you keep taking steps against the gradient, or rather against the gradient, till you hit some kind of a minimum, right? That works if your function has one nice little global minimum and or if it has many local minima and a global minimum, but you start off in the vicinity of the global minimum, you're going to get the correct answer. Ideally, you want the surface to have a very distinct global minimum, but we don't really know what the error surface looks like. What does the error surface really look like? Where will your algorithm actually end up going? We can't say, right? So, and when I spoke of the variance versus bias, you're really making statements about the global optimum rather than local optima in any case. So there have been a great many studies on trying to interpret what this loss function surface looks like. There are many hypotheses. So one popular hypothesis is that there are many more saddle points than local minimum, where the frequency of saddle points is exponential in the network size. Remember what a saddle point is. A saddle point is a location where the second derivative, the Hessian had a 0 eigenvalue, right? Or generally there are some directions where this function is going up, other directions where the function is going down. Right? So it doesn't need to have a 0 eigenvalue. The Hessian is indeterminate. It has some positive eigenvalues and some negative eigenvalues. Then another hypothesis is that if you have the loss function has many local minima, but they are kind of equivalent in that they give you the same loss, the resulting network is going to operate more or less the same. This is only for very large networks, it's not true for small networks. Now, we don't really know what the loss function looks like. What we do know is that saddle points do tend to be fairly common, things like these. It looks like a saddle, right? And gradient descent, when you say backpropagation, gradient descent using backpropagation to compute derivatives has this nasty habit of just getting stuck in saddle points very frequently. So trying to just sort of interpret what the loss function looks like, you have so many different papers. Baldi and Hornick in '89, they say an MLP with a single hidden layer has only saddle points and no local minimum. On the other hand, Dauphin in 2015 it says it has an exponential of number of saddle points in large networks. Chomoranska, I think that's how it's pronounced. For large networks, most local minima lie in a band and are equivalent. Schwartz et al. Local minima in networks of finite size trained on finite data, you can have local minima. So you have many of these papers saying seemingly contradictory things, but really they're looking at different conditions. They're all formally derived. The point is it's really hard for us to know what that error surface we are working on looks like. And so we're going to have to fight against this potentially nasty nature of the error surface when we implement our gradient descent algorithm, because we really do want to get close to a global minimum in value if not in position, right? So to close the story so far, neural nets can be trained via gradient descent. That minimizes the loss function. Backprop can be used to derive the derivatives. Backprop is not guaranteed to find a true solution, even if it exists. For large function networks, the loss function may have a ridiculous number of saddle points, which makes the whole thing much more challenging. So the issue really is, okay, fine, we know how to compute derivatives, we know what a gradient descent rule is. How do you make the gradient descent rule, which employs these derivatives, actually find you a minimum, such that the network actually computes the function or approximates the function that you want it to compute really well? Now, we will deal with these convergence issues in the next class. Right? Any questions? So, we actually have a guest lecture on Monday. So our next class is going to be on Wednesday, but do be here on Monday for. So do be here for the lecture on Monday. This is by Mike Tarr. Mike Tarr is the head of psychology, and he does a lot of amazing work on modeling the brain. And specifically, he's shown how some kinds of artificial neural networks learn representations that are kind of very similar to the representations that the brain actually computes. So remember, we started the whole class by claiming that neural networks somehow approximate the brain, right? He shows it, at least through studies, and he's done a lot of really cool work. And if you are lucky, you might just manage to get to do a project with him if you can convince him that you would work on it. And if you do that, you might just end up getting a paper in Nature or Science. So I'd highly recommend it.